So last time we looked at the Jacobi method for iteratively solving linear systems. Today we're going to look at an improved method that's known as the Gauss-Seidel method. So recall with the Jacobi method, when we solved each of the equations for the diagonal value of x, so xi is equal to some terms, on the right hand side we always used the old iterative values of x. So with Gauss-Seidel, what we do is we do something very similar, except as soon as we've calculated an updated value, we can use that on the right hand side. In other words, we're using our new guesses of xi, our new iterative values, wherever it's possible to do so. And so what that means is, if we take the Jacobi equations that we looked at last time, and we say, okay, for x1, we don't have any new estimates yet. This is the first iterate that we're trying to calculate. We have to use the old value of x2, the value at m, value of x3, and value of x4. They're all the previous iterations. When it comes time to look at the new iteration for the value of x2, well, we've already calculated x1, so let's just use that in the equation for x2. But we haven't calculated x3 or x4 yet, so we still use the old values of that. When we come down to look at x3, we also already have x1 at the new iterate. We've now just calculated x2 at the new iterate, so we can use that in there as well, and the only old value we need to use is x4. And finally, when we come down to calculate the new iterate of x4, we can see we've already got the new iterate of all of the x's, all of the other x's, so we can use them on the right hand side. Now this assumes that you're calculating these things one at a time. So that means you can't use MATLAB vector notation to do this computation because it will do all of them at the same time. So you can't use a MATLAB vector notation to do Gauss-Seidel. You have to do it one unknown at a time. So in general, just like we could for the Jacobi iteration, for n equations we can write the Gauss-Seidel iteration in a form that looks like this. This is just a indicial equation for all of the unknowns and vectors. So xi at m plus 1 is equal to 1 on aii, that's the diagonal, multiplied by the right hand side b, multiplied by this sum of terms where all of the terms where j is less than I, in other words j goes from 1 to I plus 1, we use the new values, and for all subsequent values, in other words j goes from I plus 1 to n, we use the old values. So that's it for Gauss-Seidel. It's not very different, just a subtle change in how you do it. With both Jacobi and Gauss-Seidel, the key question arises is, well, how many times do we do this iteration? When do we actually stop? And so there's probably a number of different ways of doing this, but the way I'm going to suggest is that you continue your iteration until this condition here is satisfied. So let's just have a look at this. Basically defining an error to be at unknown I, its iteration, I actually called it n here, but I mean m, xi at m plus 1 minus xim, that's the difference between two iterations at point I, divided by the magnitude of the value at point I. And of course, because we don't really care whether it's positive or negative, we need to have an absolute value. And we do this and calculate the maximum value of this for all I, and provided this is less than some tolerance that we specify, and that's epsilon s, 10 to the minus 6, 10 to the minus 8, once this occurs we're going to say that this thing has changed. So the relative error is small enough. Now the only problem with this is if this thing here is close to 0. If that thing's close to 0, the difference only has to change a tiny bit and you still might get a very large number. So this is not a foolproof convergence criterion. So can we say anything about when we expect Jacobi and Gauss-Seidel to converge? Well, it turns out that you can. For both of these methods, a sufficient condition for convergence is that the matrix is diagonally dominant. And what that means is that the absolute value of the diagonal element is greater than or equal to the sum of the absolute values of the off-diagonal elements. Provided that is satisfied, then Gauss-Seidel and Jacobi should converge. They might do so slowly. If this condition is not satisfied, then they definitely won't converge. So, in summary, the Gauss-Seidel method allows us to solve matrix problems without determining the inverse of a large matrix. It's faster than Jacobi, but it can also be more unstable. And there are other ways, other iterative solutions for solving this set of equations.